So we will be starting now. Hello, everyone. Welcome to this webinar by Imparé. My name is Anusha, and I will be the moderator for this session. So the agenda for today is to discuss Imparé's own RISC-V model. We have two main features that we will be talking about, and that is ease of integration and customizability. And for this reason, we have divided the session into two presentations to focus on each. So a little background about Imparé. We are a chip verification and a VIP development company based in the Silicon Valley. Our CEO is Faisal Haq. He is very well known in the industry, and he is the one who trains all of our engineers. And to about our RISC-V team, who are our speakers for today's session, we have Musawir Hussain, Muhammad Ali, and Afira Sohail. They have worked very hard on this model that we will be talking about, and Musawir will now be taking over.
Thank you, Anusha. Welcome, everyone, and thank you for being here. Let's take a quick look at our agenda to give you a roadmap for our time together. We will begin with the introduction, where we will provide a brief overview of what the Imparé RISC-V reference model is. Next, we will discuss the benefits of using a system Verilog-based RISC-V reference model, focusing on how it enhances verification efficiency and acceleration development. After that, we will move on the key benefits, highlighting the model's capability with UVM environment, support for RISC-V extensions and customization capabilities. Then we will focus on a comparison of the Imparé RISC-V reference model and a software-based model like Spike. Finally, we will conclude with the summary. Next slide, please. So let me begin with a quick introduction to the Imparé RISC-V reference model. So today I am excited to introduce Imparé's fully featured system Verilog-based RISC-V reference model. This reference model is designed from the ground up to meet the demands of RISC-V-based design verification. Imparé reference model acts as a golden reference model within a UVM test bench scoreboard. This means it acts as a trusted benchmark, allowing precise comparison between the expected and actual outputs of the RISC-V. So this is essential for identifying mismatches and ensuring your design adheres to the RISC-V ISA specifications. It simplifies the verification process by providing a well-structured and robust framework, accelerating timeline, and ensuring compatibility with industry standards. By doing so, it addresses key challenges faced by DV engineers, helping to save time, reduce errors, and streamline workflows. Next slide, please. So now let's look at the key benefits of the Imparé RISC-V reference model. First, it addresses a productivity gap faced by design verification engineers. Verifying advanced RISC-V-based design can be incredibly complex and time-consuming, but this model bridges that gap by providing a purpose-built solution optimized for RISC-V-based designs verification. Second, the model avoids the need for integrating software-based tools like Spike, which are not inherently designed for hardware verification. Such tools require cumbersome DPI connection, which add complexity and slow down the verification process. By eliminating these dependencies, the Imparé model streamlines workflow and ensure a smoother experience for verification engineers. A third being system Verilog based, it directly integrates into UVM environment with the overhead of additional tool or manual effort. This seamless integration simplifies verification tasks and significantly improve efficiency, allowing engineers to focus on validating the design rather than managing tool chains. Lastly, by removing bottlenecks and accelerating the overall verification process, this model shortens verification and validation schedules, a faster time to market, giving you a competitive advantage in delivering RISC-V-based designs. So now let's go over the key features of the Imparé RISC-V reference model. First, the model is built specifically for system Verilog and UVM-based verification environments. It is fully designed in system Verilog, ensuring compatibility with industry standard methodologies. The model supports the base RISC-V instruction set as well as the widely used standard extensions like multiply and divide, atomic, floating point, and compress instructions, making it our style solution for various RISC-V designs. Second, it is easy to use and integrate. This model is targeted for seamless integration into user SV and UVM test benches. It streamlines verification by making it straightforward to compare the dot against the reference model, maintaining precise alignment with the RISC-V ISA. This ease of integration and operation helps save significant time and effort during the verification cycle. Finally, the model is highly customizable. It is designed with flexibility in mind, allowing users to easily extend the functionality to support custom RISC-V instructions or unique design requirements. So this adaptability ensures that the model can grow alongside your project, accommodating specialized use case as needed. Next slide, please. So the Imparé RISC-V model is optimized for test benches. So let's compare it with a software-based model like Spike. So starting with language, the Imparé model is built in system Verilog, ideal for hardware verification. Spike developed in C++ is more suited for software simulation. For the URA model is tailored for validation hardware behavior, while Spike focusing on simulating software execution. Regarding integration, the Imparé model easily fits into UVM test benches and simulation environments. Spike, however, operates as a standalone tool or within software development framework, making direct hardware integration challenging. The Imparé RISC-V model produces a hardware-specific output like waveforms, traces, and coverage metrics. Spike's output target software analysis, including instruction traces and program output. So the Imparé model is designed for hardware verification engineer, while Spike caters to software developer and researchers focusing on software level simulation. Next slide, please. So in summary, Impare's RISC-V model is optimized for hardware test benches, implementing in system Verilog and based on the UVM framework. It's designed for easy integration into scoreboards, making test result tracking efficient and straightforward. So these features make it an effective solution for RISC-V hardware verification. Next slide, please.
Thank you, Musawir. So if you all have any questions, I would like you to please note them down as we will be moving to the second part of our webinar now. And once that presentation is over, we will be having a Q&A session where all your questions will be addressed. So Afira will now be taking over for this part of the session, which is on customization.
Good day. So before we dive in, here's a quick roadmap of this part of webinar. We'll start with how custom extensions to RISC-V, how to add custom extensions, then followed by a demo. Next, we'll touch on the possibilities for future extensions, and finally, we'll summarize the key challenges which our reference model addresses. Let's get started. Yeah, so let's explore together how to customize a RISC-V CPU model by adding your own extensions. We have developed a simple three-step method. First, select your base ISA. Choose from RISC-V R32i, RV64i, or any other based on your requirements. Then design your instruction set. Define the functionality, operands, and then coding for your new instructions. Lastly, add the implementation into your model. This can be done by breaking it down into three phases. First, you have to create class for new extension. Secondly, it includes data members like the state variables, memory elements, or any other resources specific to your instructions. Lastly, write the methods for each instruction and a decoder task to link them seamlessly. This method ensures a modular and scalable approach to the RISC-V customization. Let's move ahead to see this in action. So for demonstration purposes, our team has carefully analyzed the TCP/IP protocol and designed these custom instructions. It is very important to note that these instructions are not the part of any standard and are entirely conceptual, created to show operations. Here's how we have defined them. Immediate fields is of 11 bits, which has been reserved for potential enhancements. Destination register RD is of 5 bits, which outputs results. The source register RS is also of 5 bits, which inputs data. Lastly, the opcode is of 7 bits, which represents the operation type. The custom instructions include load header. This instruction loads the TCP header from the memory. Store header. It stores TCP header into the memory. Load field to register. Loads TCP header field into a register. Store source register to header field. It stores a source register to a specific header field. Segment data. Segments data stored in memory into TCP segments and stores them into the segment key, which is a built-in data structure. Receive segment. Receives a segment and stores it based on its sequence number. Find next acknowledge. Searches for the new sequence to acknowledge or not acknowledge. These instructions illustrate how RISC-V processor can be tailored for domain-specific applications like TCP/IP processing. Now let's move on how these are integrated into our. So let's look how to implement the TCP/IP extension in the RISC-V CPU model. We have defined a class, TCP/ISA, as you can see. This extends from the base RISC-V extension class. Then we have its two data members. First is the TCP header that stores up to 16 TCP headers. And the second is segment queue, which manages the queue of TCP segments. Then comes the instruction task. Tasks like load TCP header, TCP store field, and find next acknowledge implement the actual behavior of our custom instruction. Last is the decoder task, which maps opcodes to their opcodes to their corresponding task using a case statement. For example, 1000001 invokes the TCP load header instruction, and 1000110 triggers the receive segment, and so on. This modular implementation ensures two main things. Firstly, clean separation of functionality and easy scalability for adding more instructions in future. So by extending the base class, we seamlessly integrate this protocol-specific logic into the RISC-V framework. Next, we'll discuss the testing and validation.
Hello everyone, In this final section of presentation, I'll walk you through the practical demonstration of our model in action. I'll start by showing a simple yet powerful example, the assembly code for calculating factorial of a number. This program exercises instructions of both RV32I and RV32M extension, making it an ideal test case for our model. Next, I'll present you a short simulation video where you will see the program executing step by step. And finally, I'll share the log file generated during the simulation. This log captures the result for each instruction, verifying the correct operation of our RISC-V model. So let's get started with the RISC-V assembly. This program, here you can see the factorial program. This program effectively tests the integration of RV32I instruction for the control flow and RV32M multiplication instruction to multiply register values. Here's how the program works. Firstly, the code highlighted in yellow is used to load initial values. Firstly, we load an initial value, let's say n is equal to 5, which represents the number that we are going to calculate the factorial of. And also we are going to initialize another register with the value 1 because the factorial calculation start with the multiplication with 1. Now we enter the loop, which is shown in blue, highlighting where we iteratively multiply the result register with the current value of n. The RV32I instructions handle operations such as loading, branching, and decrementing the value of n. For example, branch equal checks if the result register is equal to 0, then it terminates the loop. And here multiplication instructions come in play for the multiplication of two registers, and I is used to decrement the value of n successively. Then jump instruction will be used to take us back into the loop, and this loop will goes on until the result the number decrements to 0. Once the loop is terminated, the result is updated with the factorial of number. So by using this combination, we ensure that our reference model handles arithmetic and branching instructions correctly. So now let's move on to the simulation video, and I'll guide you through the key events. Here you can see the simulation running. This simulation demonstrates the execution of factorial program in real time executed by our reference model. So here you can see the flow of our UVM environment, which we use for the verification of our model. And here's how the simulation is working. What we have done is initially to dump the instruction into the instruction memory for factorial program, and those instructions are fetched by our model one by one. Since this model is transaction accurate, so it will run each instruction and gives us the expected result. One thing here has to be very clear that the anyone who uses our reference model will integrate it in the scoreboard of their environment. So the question here is what makes this simulation significant is that the reference model ensures that each operation, whether it is arithmetic, branching, or loading, is executed as expected according to the RISC-V specifications. Now, let's take a look at the log file generated during the simulation. Here is the log file generated during the simulation. This log captures the result of each instruction executed by the RISC-V model and its corresponding result, allowing us to verify the correctness of our model. So in the snippet of the code, you can see initially we load the value of a number which we are going to calculate the factorial and initialize a register with the value 1. Now we enter the loop check if the number is equal to 0, then we exit the loop, and if the number is not equal to 0, then branch is not taken, and we will multiply result register with the current value of n. Then we will decrement the n value of n by 1 and jump back to the loop. This loop repetitively goes on until the n decrements to 0, and once the number decrements to 0, the loop branch will be hit and the loop will be terminated. After the termination of loop, we store the result in a register, which you can see in the log file is 120, which is actually the factorial of 5. So by capturing these and analyzing these logs, we gain confidence that our model is working perfectly fine for the real world programs like this factorial example. Now let's talk about the extensions we are working on. For the time being, we have completely implemented and tested RV32I and RV32M extensions, whereas RV32IA and RV32C are developed and are under verification, whereas the RV32ID and RV32IF will be available in the first quarter of 2025.
So, let's conclude by highlighting how our CPU reference model addresses critical challenges in RISC-V verification. Our model features a UVM native architecture specially designed to meet the unique needs of RISC-V hardware verification. It's a plug-and-play design, ensures seamless integration into existing environments, significantly reducing the setup time. The modular framework allows effortless support for user-defined extensions and project-specific configurations. Built-in compliance checks validate both functional characters and adherence to RISC-V specifications. Our RISC reference model is optimized for pre-silicon verification, helping to accelerate development timelines and enabling a faster design to tape out. This solution simplifies and streamlines the RISC-V verification process, ensuring robust designs and quicker time to market. That's all from our side. Thank you so much.
Thank you, Afira. That was a great summary. So we're done with our presentations and the floor is now open for questions. If you do have any questions, we would appreciate if you could write them into the chat box and our engineers can answer them for you.
So, hey there, guys, I have a question.
Of course, yes. Go ahead.
So, I wanted to ask, why did you choose TCP/IP for your custom instruction example?
Can you repeat?
Why did you choose TCP/IP for your custom instruction example? What's the reason for choosing that specifically?
Yeah, okay. So we selected the TCP/IP because it's well known and widely used protocol that involves various and repetitive computationally intensive tasks, such as the header processing and segmentation. This makes it a strong candidate for showcasing how RISC-V custom instructions can offload such tasks to hardware for improved performance. I hope I'm clear.
Yeah, thanks.
Yeah.
So there's another question in the chat. Afira, if you could access that.
Yeah, oh, I didn't saw that. Can this one, your factorial demonstration showed a successful run. Can you provide or explain examples of the kind of outputs you see in fail attempts, please? Right now we can't show since we showed a demo video, recorded video, so we can post it on social media or you can contact us individually, marketing team, and we can set up a meeting and discuss this further.
Hi, can you share the slides of the today presentation. Actually, I am late join. Thank you.
That will also
The
sure.
slides can be shared. Yes. We can email you the slides after the session. And yeah.
Thank you.
Okay, so since we're done with the Q&A session and we're also running short on time, I would just like to thank you all for attending our session today. You will be receiving a short feedback form to fill out after the event, and we hope to host you again for any future events that we have. Thank you.
जी अस्सलाम वालेकुम।
Hello.
इम्पारे में आप फ्यूचर में कोई जॉब्स वगैरह आ रही हैं वेरिफिकेशन इंजीनियर्स की?
So for this, you can contact us further on our emails or on our LinkedIn.
ओके, थैंक यू।
Thank you.